section of the class. Hello, good afternoon, everyone. Today we are, in the last week, we have discussed about, in the last week, we discussed about the Maxwell's equations and dispersion relation and how the optical waves interact with how the electromagnetic waves propagate in a medium. So, in that case, we saw that electromagnetic waves consist of oscillating electric and magnetic field propagating through space, correct? So, characterized by their wavelength, frequency, and speed. They encompass a spectrum ranging from radio waves to gamma rays, each facilitating a diverse range of applications in communication, imaging, and energy transmission. So, in this week, we will discuss how the electromagnetic waves interact with material. So if we have some medium and so suppose this is a plane wave, and if an electromagnetic if plane wave will pass through this medium, how light will interact with matter. So we will in this week we will understand that how electromagnetic wave interact with matter and how it is crucial in fields like material science, optics, and photonics, since it will influence the development of new technologies like in lasers, sensors, and telecom systems. So, these interactions, like when this plane wave will interact with my medium, either it can reflect or absorb or transmit. So, this will affect our performance in various applications. So, what is the objective of this week? This week's objective are to grasp the fundamental principles governing electromagnetic wave phenomena, recognize their interaction with different materials, and appreciate the practical implication and advancements in nano and quantum photonics. So, the first part is first of all, we will just review what are the lectures regarding that, and then we'll solve our assignment too. So, first of all, the key processes in wave matter interaction. So, we can understand that when will when the light will interact with our medium. Suppose we have some glass slab, and then it is coming. Then either it can reflect back, reflection, then it can transmission. It can transmit. So, when will reflection happen? What is the reflection? So, reflection occurs when electromagnetic waves encounter a boundary, causing a portion of the wave to bounce back into the original medium. So, here it was air, here n is equals to 1.5. Then some part of the wave is reflected back into the air and into the original medium. So this phenomena is essential in optics, influencing the design of mirrors, coatings, and other reflective materials that controls light paths in application ranging from imaging to solar energy harvesting. The second phenomena that can happen when the EM wave will interact with the medium, that is absorption. So absorption happens when the energy of EM waves is transferred to matter. So then it can generate some heat, or it can excite some electronic excitation. So these type of absorption, the strength of absorption is quantified by the extinction coefficient. So that will allow for the characterization of materials and their capability to convert light to other forms of energy. And where can we find the application of this? So this is an important phenomena for photovoltaic cells and photothermal therapies. The third case is, so for the absorption, we have this E of xt is equals to E naught exponential iota kx minus omega t. So if we will have some medium, in medium, this k is equals to n omega by c. So where we have n is a, so we know that n can be complex. So n will, we can write it this n plus iota k omega by c. So if we can substitute the value of k. So here this k is wave vector and this kappa is extinction coefficient. So what will have the value? Ext is equals to E naught exponential iota n omega by c x minus omega t. So we are just substituting here the value of k. So we can we can separate it into real part and imaginary part. That is exponential minus kappa omega by c. So this is extinction coefficient. So here we can see that this is the oscillating part and this represents the decaying part. So if we want to find out the intensity of the light of EM wave, it will be just the modulus of electric field ka square. So then this is proportional to exponential minus 2 kappa omega by cx. So then we can represent it as exponential alpha x. So that alpha is our absorption coefficient. So then we know if someone asks us to find out the absorption coefficient, so we have now relation for alpha is equals to 2 kappa omega by c. So we know that omega is equals to 2 pi nu. So 2 kappa 2 pi nu, then c. So nu is equals to c by lambda 2 kappa by c 2 pi c by lambda. C cancels out and it will give us 4 pi kappa by lambda. So this is the value of alpha. So, and the next thing is, the one important property is R plus T. So according to the conservation law, if the light is interacting with the medium, if the EM wave is interacting with the medium, so the sum of the reflection, transmission and absorption should be equals to 1. So this was one part regarding how our electromagnetics waves can interact with the medium. So these three were primary processes. So apart from that, there can be scattering if the medium has some scattering centers. So we know that light is blue because of the scattering phenomena. And so in scattering also there are two different types: elastic scattering, inelastic scattering. So in elastic scattering, there is no loss of energy. So if blue wavelength is hitting the molecule and blue rays are getting scattered, that is, there was some frequency and there is no loss of energy, then it will be elastic scattering. And if and in inelastic scattering, there will be some loss, and it is because of, so when our electromagnetic wave hits some molecule, some vibrations occurs, and it is converted into some heat, that is, some energy is absorbed in a molecule, and that results in inelastic scattering. So the general example for inelastic scattering is Raman scattering. So so apart from scattering, there is one phenomenon also known as luminescence. So in which you are incidenting high energy photon, and it will excite some certain levels in the material, and then the energy will be re-excited. So suppose here we have two levels, and will come, some electrons will move to upper state. This is our ground state, this is our E1. So then when the transition will happen from upper, so when the electron will de-excite, then it will emit some energy. So this process is excited, will be re-excited at slightly lower energy. So this is called the luminescence. So basically, scattering light and luminescence. The key difference between these two processes is scattering is a short time process at a femtosecond scale. Scattering, short time process, femtosecond scale, whereas luminescence is a long lived process in the order of nanoseconds. So these were three primary processes, and the two were the extra processes. Then we define what can be type of the optical material. So we can define, we can classify our material based on the band gap. So on the basis of this, we classified into three parts: semiconductors, insulators, and metals. So materials, this classification is crucial for understanding their electrical and optical properties and dictates their usability in various applications in electronics, photonics, and energy conversion. Then, what is energy band gap? So, energy band gap represents the energy difference between the valence band and conduction band in a material. So, a smaller band gap correlates with higher conductivity and better absorption of photon. So, if we have these two bands, suppose this is VB and this is CB. So our photon is coming, and this is our band gap. So, and this photon suppose have energy h nu. So if h nu is lesser than Eg, if the energy of photon is lesser than our band gap, it will not interact with the material because the energy is not sufficient to excite an electron from the valence band to the conduction band. So these photon will just pass by, that is transmit. So this photon will just, the process here will be just transmission. And if the photon energy is very large as compared to our band gap, then what will happen? The photon will interact with our electron, and the electron will move from valence band to conduction band, and that is that photon has been absorbed, and that energy is transferred to the electron to move from valence band to conduction band. So it means photon will interact with electron, energy is transferred to electron, and photon is lost or absorbed. So So then what is the impact of band gap on photon interaction? The band gap plays a significant role in determining how photons interact with materials. Photon possessing energy greater than the band gap can excite electrons across the band gap, leading to phenomena such as absorption, photoconductivity, and illumination, thus influencing the device functionality in photonic application. So to explain this, like, we have the Lorentz model, which is helpful to understand the role of electric fields, how the material will affect under the influence of electric field. So the first thing is, if we have an atom, so in the that is the explained by the Lorentz model. So in the Lorentz model, atoms are depicted as system of charged particles, that is electron and nuclei, and that can oscillate. This oscillation can be thought of as a simple harmonic motion where electrons respond to perturbation caused by the external electric field, leading to characteristic material responses to electromagnetic radiation. So then how can we understand? By spring mass analogy. Then it was the interaction between the electron and nucleus can be represented by a spring mass system, where the nucleus act as a stationary mass, and the electron represent the mass connected to a restoring spring. This analogy captures the forces acting upon the electron and helps elucidate their oscillatory motion under the drive from electric fields. Then, what is the role of electric fields? The electric fields induce motion in the oscillating charge of the electron, provoking a displacement in its equilibrium position. So, this displacement is crucial since it will generate a dipole in the material. Suppose we have material, we are applying electric field, then it will a dipole moment will be created, and which will lead to polarizability of the material, which fundamentally alters how materials react to the incoming light. So for that, we derive one expression from, like, how the susceptibility, how the plasma frequency is related to our permittivity. So the permittivity is dependent on the frequency. So as a permittivity as a function of omega is represented by 1 plus chi ne square upon m epsilon naught into 1 upon omega naught square minus omega square minus iota gamma omega. So here this term, so this omega p squared is equals to ne square by m epsilon naught, and gamma is the loss. Omega naught is the resonant frequency of resonator. So this expression is very important, and it is derived from the Lorentz model. So, and we know that polarization P is equals to epsilon naught chi E. So here this is a macroscopic response. And how can we define phi? How can we define this? Collision time equals to 1 upon gamma. So one important thing that I want to describe here. So we saw that here this is omega. So at omega is lesser than omega p. So when the frequency is the less and our wavelength is in range of 10 micrometer, 8 micrometer, 9 micrometer, that is higher reason this phonon electron collisions will dominate. And at omega is very greater than gamma. So whenever the frequency is very greater than our loss, then omega is equivalent to omega p, and epsilon omega is equals to 1 minus omega p square upon omega square. So in this case, our matter start behaving like a dielectric. So we have two models. One is the Lorentz model that tells us that describes the optical properties of dielectrics. Then we have Drude Lorentz model that describe the optical properties of metals. So next is so moving with the property that omega is greater than omega p, or at low frequency which oscillations will dominate. So now we will understand how can we describe the class through oscillator responses. So first is electronic oscillators. So these oscillators arise from the dynamics of conduction electrons in a material. The response to electric fields form the basis for understanding electrical conductivity and optical absorption features essential for designing modern optoelectronic devices. Then is vibration oscillators, that is less. So if there will be lattice vibration, then we say it's phonon. The quasi particle is phonon. So phonons are quantized mode of vibration within a lattice structure representing a critical pathway for thermal and optical properties in solids. So their behavior profoundly affects heat capacity and light absorption in materials, especially under varying temperatures. The third is rotational oscillators and their significance. So rotational oscillators link to molecular rotation in materials. So these will dominate in the microwave region. These will be IR region An electronic oscillator is UV visible reason. So, rotational oscillators linked to molecular rotation materials contribute to the material's overall response to light, particularly in complex molecules of solids. So, their implications stretch into advanced applications, including spectroscopy and phase transition. So, this was all about the lectures. So, in this week, we studied regarding how the optical response, how will, how, what will be the optical response when the light will interact with the matter. So, the first question is a beam of light is incident on a dielectric slab with refractive index. So, here you can see that refractive index is complex. If R and T represent the reflection and transmission coefficients, which of the following is correct? So, here n is equals to n plus iota kappa. So, this is real part, it is 1.5 and k is zero point 0.5. So if k has some value, it means there is some absorption. There is some loss in the system, loss of energy when the light is interacting with our material. We know the equation R plus T plus A equals to 1. So here k is equals A is equals to zero point 0.5. So R plus T is equals to 1 minus A. So in the first option it is saying that R plus T equals to 1. So from this we can clearly see that R plus T is not equals to 1, it is lesser than 1. So in the second thing R plus T is greater than 1. Obviously not this quantity cannot be greater than 1. Third option R plus T is less than 1. So this option is correct since we have some absorption value that is zero point 0.5 and it R plus T will be lesser than 1. And the last option is T is equals to zero point 0.8. So if the absorption is zero point 0.5, so the remaining R plus T is equals to zero point 0.5. So obviously the transmission cannot be equals to zero point 0.8. So the option C is correct. So we can say that the due to presence of absorption, imaginary part of n in the electric slab we get this value. Then next moving on the second question. So what is second question asking? The frequency dependent dielectric response of a material can be described by the Lorentz oscillator model. Refer to lecture 2.2 on the course playlist on YouTube. So in the second lecture we talked about the Lorentz model and the derivation of that, which gives both the real and imaginary parts of the relative permittivity. Given the real part of the dielectric constant shown in the figure below, identify the correct imaginary part epsilon double prime from the options A to D shown in the figures on right. So if we remember the what is so epsilon omega is equals to epsilon prime So for epsilon prime, so we read some conditions. So I will just talk about the real part also. So we have that equation. We have this equation that epsilon is equals to 1 plus chi plus omega p square omega naught square minus omega minus iota gamma omega. So then this equation, so we know that if we substitute 0 value epsilon 0, we have 1 plus chi plus omega p square by omega naught square. And if we substitute epsilon infinity, that will give epsilon 1 plus chi. So we know that epsilon 0 is greater than epsilon infinity. So in this case, we can see that this value is epsilon 0 is greater than epsilon infinity. So this part we have given where gamma by omega naught is 0.25. Now we want to find out for the epsilon double prime. So in the first kit we can see that omega by omega naught has a sharp peak around 1. So from the lectures and from the we can say that for the epsilon double prime also we will have for epsilon double prime we should have sharp peak around 1. Okay, so the answer can be A or B since you can see that in the figure C the resonance is has sharp peak at omega for omega by omega naught equals to 2. That is not possible. So this is wrong. For D, there is a very broad peak. So we can see that the gamma by omega naught is 0.25 and it is it has resonance around 1 and it is very sharp. So for epsilon double prime, for the imaginary part of epsilon, there cannot be this broad peak. So this has very broad peak. And between A and between B, so B is possible if we have some gain. So if there is no mention here, there is nothing mentioned here regarding like we have a gain medium. So we are considering that there is some absorption. So for absorption, there cannot be a negative dip, negative sharp peak. So here the option A is correct, which has the sharp resonance for the frequency omega by omega naught equals to 1 and then the third question is the images below capture the dielectric response of a hypothetical material for the specified damping coefficient gamma by omega naught. identify the plot that correctly represents the behavior depicted by the Lorentz oscillator model. So now, like we talked about epsilon 0, epsilon infinity. So again, I'm writing the formula, that is epsilon omega is equals to 1 plus chi, that is epsilon infinity, plus omega p square omega naught square minus omega square minus r to omega. So where epsilon 1 is equals to 1 square minus k square. So now in the figure A, so we are given chi is equals to 10 and gamma by omega naught is equals to 0.05. So in the figure A, we can check epsilon 1. So you can see that this part is epsilon 0 and this is epsilon infinity. So option A, epsilon 0 is lesser than epsilon infinity, which is unphysical, not possible. Since epsilon 0 is equals to 1 plus chi plus omega p square by omega naught square and epsilon infinity is equals to 1 plus chi. Then similarly in figure D also you can see that epsilon 0 is lesser than epsilon infinity. So these two are options cancel. So now option B and option C. So same in option B we have epsilon 2 is equals to negative. This is fine. Epsilon. So first condition are satisfied by B and D. B and C both the option, that is epsilon 0 is greater than epsilon infinity. Epsilon 0 is greater than. Now we will talk about epsilon 2, that is epsilon double prime imaginary part. So in this case it is negative, and but we have given some gamma by omega naught, that is, so given gamma by omega naught is equal to 0.05. Some absorption, there is not gain. So epsilon double prime can't be negative. So this option is also cancelled. Then option C, since epsilon double prime is equals to positive and it is satisfying both the condition that epsilon 0 is greater than epsilon infinity and epsilon double prime is positive. Now moving to the next question. Consider the schematic wavelength dependence of refractive index for the material silicon dioxide SiO2 and gallium arsenide, and given below are the statements regarding them. So you can see that we are provide we have been provided the real part of the refractive index as a function of wavelength. So which of the statements are true? So we have two statements that gallium arsenide has a higher refractive index than SiO2 due to its smaller band gap and stronger electronic polarizability. And the second statement is the refractive index of a material increases sharply at shorter wavelengths due to strong photon absorption. So First, we will see the first statement. What is it saying? That gallium arsenide has a higher refractive index. So we can see that for gallium arsenide, we are given that n is equals to 3.8 something, and for SiO2 n is equals to 1.5. So clearly we can say that so clearly we can say that n gallium arsenide has n SiO2. And the second statement is, so we got this S1 is true. The refractive index of a material increases sharply at shorter wavelength due to strong phonon vibration. So we can see that here, we can see that the refractive index of a material is dropping here. It's not increasing. Here it's suppose 9 micrometer, and there will be phonon vibration. So the phonon vibrations, and so around phonon vibration there is not increase in the refractive index. It is here. There is the sharp increase in refractive index. So the statement S2 is incorrect. And this is, and this is an UV visible region. So just now, before starting the assignment, we have read that at around in higher region there will be phonon vibrations, and in the UV invisible region there will be electron oscillations. So there we can see that there will be a sharp increase in refractive index in the UV visible region, not in the phonon vibrations. And with this graph also we can know that the next plot will become like this. So next question is related to this graph only. So this is saying that in certain wavelength region, the refractive index of a material shows minimal variation, while in the other region, it changes rapidly. So we saw that in that region, it was constant, and in this region, there is sharp increase. So we can see that in this, if we consider region 1 and region 2, in one region, Ri changes rapidly in this region. Minimal variation. So S1 is true. Then in second case, a sharp change in refractive index near a specific wavelength often indicates a resonant interaction within the material as described by the Lorentz oscillator. So we saw that. So strong absorption. So if the energy of the wavelength, if energy of the photon is greater than the band gap, then that photon will interact with the material and it will show a strong absorption, and then there will be a strong change in refractive index. A strong absorption is always accompanied by strong change in refractive index. So the statement S is also true. So both in that case both statements 1 and 2 are true. Next question. So what will be the likely best guess from options given? Refractive index at 1064 nanometers. So for that case, you can see that this is also related to the previously diagram which was for gallium arsenide, whose refractive index was between 3 and 4. It was 3.8, so I'm assuming that here it is 3, it's 4. So it was like this. So we know that away from resonance, k is equals to 0. So among all the options, there's only one option which have this condition, because we know that the resonance was around, so we can refer figure for questions 2 to 4. So for the gallium arsenide, it was like this. So away from the resonance, it was going tip. So we know that if our resonance is around 1 micron, then we have the k value is 0 around. Away from the resonant value, the k will be 0. So the best option is C. If it is asked around the resonant frequency, then we could consider the minimal gamma value, minimal k value, that is 0.13. But since there is no reference figure for the resonance, but still we are considering that the figure for 4 to 5, and we are considering the refractive index of gallium arsenide. So we can say that, okay, in that case, the resonant frequency is not at 1064 nanometers. So the answer is C. Next question is the absorption coefficient alpha at wavelength 532 and 1064 nanometers is respectively. So we derived the formula for alpha, which is given by alpha is equals to 4 pi kappa by omega. This is extinction coefficient. So in that case, we are not given kappa, we are not provided extinction coefficient, we are not provided. So how can we solve this question? So again, we will consider the plot and we will see that for 1064 nanometer, we are far from our resonant frequency. So alpha will be 0. So among these options, there's only this condition. By considering the gallium arsenide plot, if we see that the resonance is not around 1064 nanometers, so alpha is equal to 0 for that. And for 532 nanometer, there will be some value, some positive value, which will have the dimensions of meter inverse. So if we are considering, suppose if we consider the second plot, that is for SiO2 plot, but in that case we can see that 532 nanometer and 1064 nanometer both are away from resonance. So both should be 0, but there is nothing such option. So we are considering the gallium arsenide refractive index plot and saying that okay, 1064 nanometer, for 1064 nanometer the alpha will be 0, and for 532 nanometer there will be some absorption coefficient. So the option A is correct. Next question is, group velocity is given by the formula Vg is equals to delta omega by delta k is equals to C by n plus omega delta n by delta omega. So we know that n refractive index is the frequency dependent, and the group velocity will be equal to the phase velocity is equal to C by n only when the refractive index is independent of frequency. So we can also see from this formula that delta n by delta omega will be 0. Vg is equal to C by n. That is equals to our phase velocity. So given the plot of the refractive index versus frequency with three marked regions A, B and C, in which regions is the group velocity the highest? So we have to tell about the dielectric constant. So after seeing the dielectric constant versus frequency plot, we have to say that which group in which region the group velocity is higher. So Vg is given by C upon L plus omega delta n by delta omega. So from this formula, we can say some things, that is Vg or group velocity will be high when, first case, What is first case? If n is small, so it's in denominator. If denominator will be small, Vg will be high. Second case, if delta n by delta omega is small, or if it is negative. So in reason, we know that n is equals to root of epsilon. So if the epsilon value in this case it is higher, then n value will be higher. Similarly in C case, so in region A and C, there is, we can see that in region A and C, our epsilon is nearly constant. So if the epsilon is constant, what does it imply? That there is weak dispersion, and weak dispersion will imply high Vg. In region B, we can see that this there is sharp variation in epsilon, which will create the strong dispersion. So from this we can say that in region A and C, since our the dielectric constant is constant, there will be weak dispersion. That implies the high group velocity. So in the region A and C, the group velocity will be higher, and in region B, the group velocity will be low. Next question is, consider an ideal lossless Drude model, Drude metal with plasma frequency h cross omega p is equals to 5 electron volt. Calculate the wavelength at which the permittivity is equals to 0. So we are given that h cross omega p is equals to 5 electron volt, and we have to find out the wavelength at which the permittivity is 0. So for a lossless metal, epsilon of omega so the condition we have to find out, so we are provided that this is 0, so it implies that omega is equals to omega p. So now E is equals to SC. So we are given the H prime H cut value, and we are given the h5 into, so the unit of h cut is in joule seconds, and we are given the energy in electron volts, so we will multiply it by the electronic charge, which is 1.6 into 10 raised to the power minus 19, to convert into joule second. So we want to find out the wavelength, so it will give us 247.5 nanometers, which is close to 235 nanometer. So C is the correct answer. So the next question is, the electric field of a X-polarized electromagnetic plane wave propagating in plus g direction can be expressed in either of the following two conventions. Ex is equals to Ex naught exponential minus iota kg plus iota omega t, and the second is Ex is equals to Ex naught exponential iota kz minus iota omega t. If the wave is propagating in an absorbing medium, so this is the crux of this question, that it's given that we are considering the absorbing medium, which has the refractive index n is equals to n dash plus iota n prime. So we have to find out which of the following is true. So to solve this question, what we have, the equation is E is equals to E naught okay. So for it is given that it's an absorbing medium. For absorbing medium, and double prime will be 0, greater than 0. So we are given that k is equals to n omega by c n prime plus iota and double prime, so which is k prime plus iota k double prime. If we will substitute this value of k, suppose in the first equation I am substituting that, E is equals to E naught exponential minus iota k prime k double prime z plus iota omega t. What we will get? E naught exponential minus iota k prime z plus iota omega t and exponential k prime z. So because iota is minus, iota square minus 1, and there was one sinus outside, so it is plus 1. So if it is given that this is an absorbing medium. So from this equation, we can see that k prime is greater than 0, which is physically not possible. So wave should decay if it is an absorbing medium. Wave should decay with propagation, right? Okay, so to ensure that to ensure this k prime must be less than 0, which implies that n plus is less than 0. So for the first case, we found out that n prime n double prime is negative. In second case, we have given this was for first. E naught is equals to ax naught exponential iota kz minus iota omega t. So for that, if we will substitute in this equation, we will get iota k prime z minus iota omega t into exponential minus k double prime z. So if the wave is propagating in an absorbing medium, the wave should decay. So it automatically, this vector is showing that decaying wave, that is k prime is less than 0. So to satisfy this, k prime is greater than 0, then n double prime is greater than 0. So n double prime is equals to positive in this case. So in this case, we can see for this question, we can comment about n double prime. So for first case, n double prime is negative, and for the second case, n double prime is positive. So option 5 is correct. These are the equation we derived, which have we have already derived. So now we will take a 10 minutes break, then we will move to the some exercise from the Mark Folks book. This is all about the assignment. Then there are two or three questions regarding, and then we will revise one part of the lecture, which is metamaterials. That why do we need metamaterials, and what is different from the general part. So we will discuss something about this. We will start after 10 minutes. Okay, so now let's start the textbook exercise, which is taken from Mark Fox chapter 2. So, in this question, what is asking the complex dielectric constant of the semiconductor cadmium telluride is given by epsilon r is equals to 8.92 plus 2.29 at 500 nanometer. So we have given the complex, we have provided that complex permittivity. So calculate for CDTE. Okay, so we have to calculate for cadmium telluride at this wave 500 nanometer. We have to calculate the phase velocity, absorption coefficient, and the reflectivity. So we have n is equals to 1 by root 2 epsilon 1 plus epsilon 1 square epsilon 2 square 1 by 2 1 by 2 and k is equals to 1 by root 2 just with the negative sign. Okay, so if we want to find out, so first part is phase velocity Vp, that is given by C by N. So to find out Vp we need N. So we can find out N using equation 1. We can find out N using equation 1, and that will provide me 9.97 into 10 raised to power 7 meter per second. Just by, we can just, we know that epsilon 1 is equals to 8.92 and epsilon 2 is equals to 2.29. So next is, second part is absorption coefficient, that is alpha. So what is alpha? Alpha is equals to 4 pi kappa by lambda. So for that you have to find out this n plus iota kappa. So for this we need k only. Lambda is given, that is 500 nanometer. Then we have to find out the reflectivity. So after solving this, we will get the alpha is 9.6 into 10 raised to power 6 meter inverse. Then third part is we have to find out the reflectivity. So reflectivity is given by R n minus 1 square plus k square n plus 1 square plus k square. So now we have both the values. We have calculated n from equation 1, k kappa from equation 2, and just by substituting the values of n and k, we will get the reflectivity value, that is 25.6%. Okay, so next question is the question that solution. Hmm. So the next question is asking the detectors used in optical fiber networks operating at 850 nanometers are usually made from silicon, which has an absorption coefficient of 1.3 into 10 to the power 5 meter inverse. So we are given alpha, that is 1. Alpha is equals to 1.3 into 10 to the power 5 meter inverse at this wavelength. So lambda is equals to 850 nanometer. The detectors have coatings on the front surface that makes the reflectivity at the design wavelength negligibly small. So calculate the thickness of the active region of a photodiode designed to absorb 90% of the light. So 90% of the light is absorbed, and we have to find out the what is the length of the thickness of the active region. So exponential minus alpha x, so that will give us the alpha l. So since 90% of the light is absorbed, only 10% light is transmitted, so we in the output it is 0.1. So by using this we can get the value of l. So the solution, so first we use these two equations, we substitute the values of n and k, and we got the desired results. The second thing is anti-reflection coatings. So 90% of the light is absorbed when exponential minus alpha L is equals to zero point 0.1 at the operating wavelength. So with alpha is equals to 1.3 into 10 raised to the power 5 meter inverse, we can get the L is equals to 1.8 into 10 raised to the power minus 15 meter, that is equivalent to 18 micrometer. So this was the exercise, and there is one more question. Yeah. So then the next question is, a solid has a single absorption band of width gamma centered at frequency omega naught such that the extinction coefficient may be written in the form of k omega is equals to gamma naught omega naught in this reason. So in this reason we are given kappa naught, otherwise 0. So we have to calculate the refractive index at low frequencies when omega naught is very greater than gamma. So we know that. So we are asked to compute the refractive index at low frequencies. So if it is given that omega naught is very greater than gamma, it also means that we can assume that omega naught is very greater than omega. So we can substitute omega is equals to 0 in the Kramer's Kronig relationship. So what? So these were the relationships. If we know the one part, if we know the real part, then we can find out the imaginary part, and the vice versa. So on substituting this, so we had these two equations. We got these are the Kramer Kronig relations. So n omega minus 1 equals to 2 by pi, and polarization 0 to integration is along 0 to infinity omega prime k omega kappa omega prime upon omega dash square minus omega square d omega prime. So if we will substitute this equation into, and using the fact that kappa omega is 0 at all frequencies apart from those within the absorption band, so we can write n naught. So we will substitute omega is equals to 0. So what will this equation will become? N naught is equals to 1 plus 2 by pi, and we have provided the limit. So kappa at 0 is kappa naught, and omega dash square d omega dash. So omega dash 1 omega dash cancel. So in the integral part we have this value 1 plus 2 by pi kappa naught upon omega dash d omega dash. So now if we are considering that omega naught is very very greater than gamma, we can assume that omega dash is equals to constant, that is equivalent to omega naught. So we can get the integral. We can take this constant value outside the integration 1 by 2 by pi kappa naught omega naught, and in the short, what is the limits? Omega naught minus gamma by 2 to omega naught plus gamma by 2. So omega naught plus gamma by 2 minus omega naught plus gamma by 2. So omega naught to omega naught cancel, and we will get gamma naught. So gamma we will just multiply by gamma. So we got the value n as omega equals to 0, 1 plus 2 gamma kappa naught by pi omega naught. So this is the desired answer. The next question is, so this was all about the exercise and the assignment. So now we will revise just one lecture that will be helpful for the next assignment, and the why are we doing nanophotonics. So up to Kromer Kronig relations, we have solved the problems. We have discussed a lot of things about how our electromagnetic wave, how electromagnetic wave will interact in a medium. So now what up to now we have talked about the naturally occurring materials. So now we will talk about how can we engineer the optical response of materials according to our need. So we want to design our materials such that we want to engineer our materials such that we can tune the frequency we desire, we can confine our light. So the goal of nanophotonics is to engineer optical response according to what we want. So in naturally occurring materials, electric and magnetic response is limited. The optical response is not tunable. Possibility of nanofabrication patterning is limited. So you can see that there is a quadrant form that, so in the first quadrant where epsilon is greater than 0, mu is greater than 0. In this scenario, the category is most, so most dielectrics lie in this category only. That is, we have some positive epsilon and some positive permeability. Then if there are some materials where epsilon becomes negative but permeability is greater than 0, so it means there are some metals. So this condition is satisfied by the metals. So metals or some doped semiconductors comes along this category. Then if epsilon is positive but permeability is negative, then there are also some naturally occurring magnetic materials which comes in this category, that is like some ferrites. Now in the last or fourth quadrant where epsilon is negative, like permittivity is negative as well as the permeability is negative. What does it mean? So negative epsilon. So such material doesn't exist in nature. So we fabricate our materials such that we can get this thing. So in general, the n is defined by the epsilon mu ka square root. So in optical regime, since mu is equals to 1, so the refractive index is given by only n is equals to root epsilon. So what is mean by like negative epsilon or negative refractive index? So negative epsilon means your polarization is going to be in opposite direction to the electric field, that is out of phase to the electric field. So this is represented by this phasor diagram in which the real part is both a function of epsilon mu, imaginary is along y-axis, both is a function of epsilon mu. So the phase is, so if the epsilon tilde is equals to epsilon 1 plus iota epsilon 2, it is given by modulus, that is the amplitude of epsilon and e iota theta. And similarly, mu is permeability is represented by the mu modulus multiplied by e iota phi. So the combined response, can be represented by the combined response of epsilon mu on the refractive index. So n will be given by modulus of permittivity into modulus of permeability under the square root, and the phases will add up e exponential iota theta plus phi by 2. So, what are metamaterials? So, the materials with engineered optical response. An optical response will consider the values of changed permittivity and permeability. So, in this case, in the first case, we can see that the regular dielectric where mu is equals to 1. So, we can see that this is a real part, epsilon, real of epsilon, which is a function of epsilon mu, and which is represented by the red part. So mu is equals to 1, so it will be along x-axis. Now, if there is some epsilon 3, so it will be in positive axis. So the blue color is representing the n. So the resultant will be the combination of both. So the black is representing the resultant vector. So modulus of n and exponential iota theta plus phi by 2. So in this case, we have seen that positive index absorption is not equals to 0, but we have such type of materials which are naturally occurring, that is regular dielectric. Then materials with magnetic response, where metals with small loss, if we are considering that, the blue line is representing magnetic response, that is mu e iota phi. Red is representing the n absent permittivity part, and the resultant n will be is represented by the black line. So n is negative, that is non-zero absorption. So in case of lossless metals, you can see that epsilon is blue, which is along the x line, negative x, and mu is 1. So the resultant n is 0. So n1 is 0. So means there is no loss. And hence we are getting the zero refractive index material. So we will study further that how can we utilize the zero refractive index materials, negative refractive index materials, and what is the applications of these materials in our day-to-day life? How can we use the nanophotonics part? So this was all about the optical responses of the. So, up to the week 2, we have covered. First, we discussed with the review of Maxwell equation, dispersion relation, then how the electromagnetics propagate in a medium, then how the electromagnetic waves interact with the medium. Thank you.